Last chapter, Eigenvalues and Eigenvectors, and this actually will lead to Diagonalization. Sometimes some authors use Diagonalization, but I normally will use Diagonalization, diagonal. Okay, so what does it mean by an eigenvector? Okay, so in this chapter, we only dealing with the square matrix n by n. You will never see m by n unless m is n. Okay, so let A be n by n matrix. Why? Because you will have to find the determinant. So we go back to chapter 1, finding determinant. Okay, let A be an n by n matrix, a non-zero matrix, or a non-zero vectors. V in Rn is called an eigenvector. Of A if AV is lambda V, AV is lambda V for a real number lambda. This is very important. Keep that in mind, that your vector cannot be a zero vector. If somehow after your calculation your vector V turned out to be zero vector or zero, definitely it's wrong. So you will know that you have done some wrong calculation. Okay, keep in mind the vector V is never zero, it's a non-zero. So AV is lambda V for lambda in R. The scalar or the number lambda is called the eigenvalue. Okay, of A corresponding to the eigenvector of V. Okay, this eigen my PhD supervisor, she's a German, okay, and she was teaching me advanced linear algebra. You remember my undergraduate linear algebra professor, John Race, okay, and then we have another course of linear algebra. It's called advanced linear algebra. Okay, in UTM, if you do master, you can have theory of matrices, something like that. She told me, she's a German, eigen comes from a German word. The same thing like Z for, I told you this in class, right? Z for integer comes from German, and Zahlen, right? This is a German word. Eigen is also a German word, and this is what it means, self. Okay, so when you mention about eigenvalues, this is this value accordingly to this vector, so they belong together. AV is lambda V means that particular lambda is for that particular V. Okay, and it is not unique. Okay, it is not unique. Meaning there can be many eigenvectors corresponding to the eigenvalue lambda is unique, but V is not unique. Okay, so lambda is unique, V is not unique, but it belongs to the right vectors. I will show you an example. Okay. First example given in the book is example 5.1. Let A be 3, 0, 8, negative 1. Okay. And you are given V is 1, 2. Question, find lambda. Okay, find lambda. So you go to the, so you have to remember this, yeah? Okay, AV is lambda V. So you multiply A by V, you get 3. Writing it as lambda V, 3, right? So AV is lambda V. So lambda is 3. Okay? So how do you get the lambda? How do you get the V? This is chapter 5. How do you get the lambda and how can you get the V? Okay? This is given already. Call it V1. Try another one. V2 is 2, 4. Okay, so try again. 2, 4. So this will be 6, 12, right? Which is 6 times 1, 2. Wait. No, I don't want 1, 2. I want 2, 4. V is 2, 4. Okay, so this is still 3. So lambda is still 3, but V can change. Actually, V can be any multiple of this. So it's span. Okay, later on you will see what is it called. It's called the basis of the eigenspace. Okay, now try another one. Cannot be 0, 0. Okay, if you try negative, right? Try negative. Maybe we put negative 1, negative 2. Okay. Negative 1, negative 2. So you get negative 3 and 3, 0, 8, negative 1 times negative 1, negative 2. Negative 3, negative 8 plus 2 is negative 6. And you put this, the original, and lambda will be 3. So you will see again, lambda is still 3, right? But V is different. So V is not unique, lambda is unique. Okay, is this the only lambda? Okay, the answer is no. This is not the only lambda. The second question is 1, 1 an eigenvector? Is 1, 1 an eigenvector? So try with 1, 1. If you put 1, 1 here, if you put 1, 1 here, okay, because it has to be lambda V, right? If you put 1, 1 here, 3, 7, right? 3, 7 is not equal to multiple of 1, 1. Okay? So 3, 7 is not equal to multiple of 1, 1. So this is not an eigenvector. Is not an eigenvector. calculate for this chapter, AV is lambda V. Now you can either move this to that side or move that to this side, but following the notes and some reference, you move to this side. So I get lambda V equal AV. Now this is 1 by 1, right? This is just a number. V is a vector. A is n by n. V is n by 1. Okay? Doesn't matter because this is just a number. When you multiply this, you get n by 1. That's why you can multiply a matrix by a vector is equal to lambda by a vector. It's n by 1. It's a vector. Okay? Now I want to move this to that side. Now, can I do this? Oops. This is not a vector, right? When you multiply is a vector. When you multiply is a vector, vector minus a vector. This is okay. Now I want to take out the V. Okay? Take out the V on the right. What is left inside? Can I write like this? I cannot write like this because this is still lambda V minus AV, because this is a number minus a matrix. How can I have a number minus a matrix? And that's why we have to multiply by I. Okay? So this is the formula actually. And to solve this, okay, V cannot be 0. Okay? The determinant cannot be not 0. Okay? If the determinant is not 0, you get a unique solution, which is V is 0. Homogeneous, right? Homogeneous system of linear equation, n by n. If the answer is unique, determinant has to be not 0. But our V is not 0. Our V is not unique. Meaning, you have to get the determinant equal 0. Okay? So this is why. That's why they get the formula. In the book, they just give the formula. So, what you do is, you get the determinant, lambda I minus A equal 0. Okay? This is to get the solution to be non-trivial, to be not unique, to be not 0. Okay, so this is what we call the characteristic. I can just put this as determinant, yeah? This is called the characteristic polynomial of A. Okay. If you put lambda I minus A equals 0, this is called the characteristic equation of A. If you do the other way around, it is okay. You will get the same answer because it's equal to 0. If you put A minus lambda I, if you refer to other books, they put A minus lambda I, it's okay. But try to be consistent with our notes. Okay, so this is how you will get the lambda. Okay, this will give you a polynomial depending on the rank of the matrix. If the matrix is 3 by 3, you will get polynomial of degree 3. Just now, our matrix is 2 by 2. So you will get a polynomial of degree 2. Okay, now The solution space is called the eigenspace. Okay. From here, when you equate to 0, you will get lambda. Okay? You will get lambda. That is the eigenvalues. That lambda, you put inside here, and then you solve, you will get V. This is chapter 2. Okay? With this V, that is the eigenvector. Then you take the span, then it becomes the eigenspace. Okay. Let's try. Okay. Another thing is, this chapter needs you to be able to remember and to find the determinant of a 2 by 2 matrix. It can be 3 by 3 matrix. I can also give you a very big matrix where you can find the determinant easily. Okay, so go back to chapter 1, finding determinant. You also need to know how to factor polynomial, because when you equate this to 0, you have to factor, then you will get the lambda. Okay, and we are dealing only with the real numbers. So if you cannot solve the polynomial, then we don't have eigenvalues as reals, because the original definition is lambda is R in R. So if you forget how to factor polynomial, you will be in trouble. Okay, so remember you learned before, I think in calculus 1, in high school, you learned this, right? So we go back to the first example. I will erase all this. The calculation is not that difficult. Okay? And for your final, it's like test 2, where you will be able to refer to the notes. So you don't have to worry about not remembering. Okay, so A is just now, right? 3, 0, 8, negative 1. Okay, now the question is, find the characteristic polynomial. This is example 5.2. Find the characteristic polynomial, eigenvalues, eigenvectors, and eigenspace of the matrix. Actually, earlier we already know lambda is 3, right? So now we have to find all lambdas. Okay. If you remember, polynomial of degree 2, maybe I just use x, yeah? We used to use x before. Okay, ax squared plus bx plus c, right? Okay, how many roots can a quadratic, right? The name polynomial with degree 2 is called quadratic. How many roots can this have? Jawab, jawab, jawab. How many roots? So if you draw polynomial, if A is positive, it will be like this, right? If A is positive. If A is negative, it will be like this, right? So if it is like this, you can have 2 roots, 2 real roots. Okay? Question is, how many roots can it have? It can be 2. Can it be 1? Can it be 0? Okay? If you want to have just 1 root, it will be like this, right? Okay? Or no root. student. Saya janji kan, early semester, every single one of you, I want you to come to the board and write something. Tak boleh dah, MCO, PKP. One time, I asked the student to draw a polynomial, a quadratic polynomial with no roots. You know how the student draw? Like this. Boleh ke? No roots. Cannot be like this because they can go out, right? So if no root means like this. Imaginary roots. Okay? This is masa sekolah dulu kan. So you have to know your polynomial. Okay? What kind of polynomial will give you this, this or this? This is quadratic. What if the third degree polynomial? How many roots for third degree polynomial? If you have fx equal ax cubed plus bx squared plus cx plus d, how many roots can this have? 3? What about less than 3? Cuba lukis. Can you draw? Okay, this one tadi example dia is like this, right? X plus 1, x plus 2, example kan? Okay, then negative 2, negative 1 kan? Right? Then you do this. This is this one. If you have fx equal x minus 1 squared, there is only one root, right? So the root is here at 1, and then you just draw like this. So the lambda here is 1, lambda here is negative 1, negative 2. What happened about no root? Fx equal like this, right? Okay, this is no root because x squared like this, and then you just add 1, right? No root. So in this case, there is no lambda. Oh, it's imaginary root, plus or minus I. You don't do this. It's all real. So in this case, you said there is no lambda. Lambda equals negative 1, negative 2. Lambda equals 1. That is your eigenvalue. Alright, back to the question. Brian, we don't have imaginary here. Forget about imaginary. We are all real. This is in a real world. Okay? So if you reply imaginary, minus 1. Minus 1 means tolak satu markah. Okay, so the answer will be 0, 1, 2 or 3 roots. Okay, now I want you to draw the polynomial with, ada ke yang 0 root ni? You said there is a 0 there, right? No, there is no 0. Okay, no imaginary. You said there's 1 or 2 or 3. Okay, try and draw. If A is positive, how do you draw like fx is x cubed, right? You remember? This like, dekat comment boleh, you can comment and put photo, or you can just type. I never try. I don't know if you can put photo at the comment, right? Okay, so this one, right? Fx is x cubed. So you can have only one root. How do you draw to get 2 roots and 3 roots? Okay, like this. Yeah, S. Okay, so this is 3 roots. What about 2 roots? It can go like this and touches. 1, 2. So this is the case when it has 1 root. So in this case, lambda is 0. Okay, this, say this is 1, this is 3, this is negative 2, so fx is something like x plus 2, x minus 1, x minus 3. Okay? So you have 3 roots. This one, if this is 2, this is negative 3, so this is like fx equal x plus 3, x minus 2 squared. But this one is actually x minus 0 cubed. All other. So this is possibilities. Okay, possibilities. This will be one of your answers for this chapter. Alright. So let's go back and find for here. Okay. So f lambda equal lambda I minus a. Okay, which is lambda 1001 minus 2 by 2. Okay. Equal determinant of multiply lambda 0 0 lambda minus 3 0 8 negative 1 equal gambar kabur. Gambar apa yang kabur? I look at the laptop macam okey je. Akmal, gambar apa yang kabur? Lambda minus 3 0 negative 8 lambda plus 1. Yang lain tengok kabur juga ke? Okay? Okay, now this is 2 by 2. Determinant of A, B, C, D is AD minus BC. Kan? Internet dia kan? Okay je kan? Okay, so this is lambda minus 3, lambda plus 1. Done. Because minus 0. Don't forget, last time I give this example in class, and then the student after that just multiply like this. This one you don't see the 0 because this is minus 0. It's not just the diagonal. This element. So this is the polynomial. This is the polynomial. Okay? This is the characteristic polynomial. So the eigenvalues are these two. Okay? Just now we have 3 as eigenvalues, but we didn't have negative 1. Now we have negative 1. Now next is to find the eigenvectors. Can A minus lambda I lah, kan saya dah sebut tadi, you can do this minus this or this minus that. You can do this also. Some books they use this, but my book I use the other way around. You get the same answer because you have to equal to 0. Okay, you get all negative. The negative of this. But when you equal to 0, you will get the same lambda. So the answer is yes. If you refer to some books, they write like this. But in my books, I write like this. Okay, so how to find the eigenvectors? So you remember last time, just now I put lambda I minus A V equals 0. Right? This is how you would solve A V is 0. And what is 3i minus A V is 0? This is the 3i minus A just now, right? So I just put 3 inside here. Okay, so 0, or you can rewrite, but it's already here, so I just put 3 in here. 0, 0, negative 8, lambda is 3, 4. V equals 0. So V is, say, xy. Okay, so just replace in here. Okay, so this is now chapter 2, homogeneous system of linear equation, right? Chapter 2. So to solve for V, you can do this, right? Okay, so R1 to R2. Hey. Okay, there's nothing left that you can do. You want to make this 1, so negative 1 over 8 R1. So you will get 1, negative a half. Okay, done. Okay. Yeah, just follow the book. Number 1 rule is V cannot be 0. Okay, in the whole chapter, V is non-zero. Number 2, after you do all this calculation to get the V, make sure you have a free variable. Make sure you have a row of zeros, because this is determining the free variable. Okay, remember this for your final. You have to get row of 0. If there is no of 0, go back. Probably your polynomial is wrong. Imagine if the whole question is 20 marks, your polynomial is wrong, you will lose everything. Okay, so what's the main point here? To find determinant. What happens if this is a 3 by 3 matrix? Okay, so this is very critical. I didn't say hard, I didn't say difficult, right? But it's important to be careful. How do you find the polynomial in the first place? Okay, lepas tu lupa chapter 2. Okay, this is x, there is an x, there is a y, right? So x minus half y is 0, y is free variable. Okay, so x is half y, so you can put xy equal half k and k in R. Or you can change the variable, because I don't like fraction. I can put this, I multiply all by 2, I get k, oh sorry, I call it c to c. This is also true, because your k can be any real number. Remember just now, when we put lambda equals 3 on page 291, you remember when we put lambda is 3, lambda is 3, V is 1, 2, right? C is 1. We also have 2, 4, right? When C is 2. It's the same lambda. So the answer is 1, 2 is the eigenvector of A corresponding to lambda equals 3. You just need 1 for this one. Okay. Sometimes one eigenvalue can give two eigenvectors if you have two free variables, but not here. Okay? What happens suddenly if the matrix are all 0? 0, 0, 0, 0. Haha. There was once a question like this, student cannot answer. Solve that. Because it's too easy, student cannot answer. How do you even write? There's nothing. Then you will put 0 equals 0. This means x is k1, y is k2. Both are free. Okay? So you will have two vectors. Okay? In that case, you get 1, 0 and 0, 1. Okay, this is not this question, this is other question. Somehow the matrix becomes 0, 0. Still, okay, so for that particular question, you can get two eigenvectors, right? Okay, so forget this, because this is not here. Now, I still need one more, right? Just now we have 1 is 3, 1 is negative 1. So I still need, when lambda equals negative 1, so I have negative I minus AV is 0. Okay, for this matrix. So I get, apa tadi? Minus I minus A, right? Minus, just now I get this, right? Kan? Okay, so when lambda is negative 1, I get negative 4, 0, negative 8, 0 again. Okay. Right? Okay, so just leave one question here, right? One. Okay. Now, this is easy because you just need 1 or 2. So negative 1 over 4 row 1 will give you 1, 0, 0, negative 8, 0, 0. And then 8 row 1 plus row 2. And you get 1, 0, 0, 0, 0, 0. Make sure you know how to write the solution. This is why we introduced this in chapter 2. Okay? And also when you solve this for kernel, right? Kernel is AV equals 0. Find the kernel. So it is something related to that. Now to solve this, you will put x is 0, y is k, right? You read this, x is 0, and you read this, y is free. So xy is 0, k. So when lambda is negative 1, you can have one eigenvector. Okay? For this chapter, you can always check your answer. You can always get full mark. Because you can check whether is this true. Just multiply A by V. Do you get 3 times V? We have tried this for this, right? So let's try for this. So AV is 308 negative 1 0 1 equal 0 negative 1, which is actually negative 1 0 1, which is actually lambda V. Yes, right? Okay, so we are done with this question. So either you write as a multiple of the eigenvector, or you just write the span of eigenvector. That is the eigenspace. This is the eigenspace. So the same thing, E of lambda is equal to K01, right? Or you can put this as span of 01. Okay. Now we go to the next one. Naik pangkat sikit. Repeat example 5.2 with a different matrix. Okay. Now A equal 3 by 3, 5, negative 8, 1, 0, 0, 7, 0, 0, negative 2. Dapat di mana ni? Is that the right matrix? Where did I get this from? Oh, ni dah section lain. Sorry. Oops. 3, negative 2, 0, negative 2, 3, 0, 0, 0, 5. Okay. Now F lambda equal lambda I minus A. Saya nak bagi trik sikit, shortcut. Rather than multiplying just now lambda by 100, 010, 001 minus A, this is the trick, yeah? The diagonal is lambda minus. Okay, the diagonal is lambda minus. The rest is the negative because it's lambda I minus A, right? So the rest of the diagonal are all zeros, minus A, so it's the negative. So this becomes 2, 0, 0, 0. Tak nampak sangat because so many zeros. Okay. O2. Imagine if this step is wrong. Okay. Imagine if you copy wrong. Satu markah ni, satu soalan ni 20 markah tau. So maybe better to double check from the beginning, yeah. 3, negative 2, 0, negative 2, 3, 0, 0, 0, 5. Okay. So lambda minus 3, lambda minus 3, lambda minus 5. Then the rest is the negative 2, 0, 2, 0, 0, 0. Okay. Now, you remember chapter 1. How do you find the determinant? What do you call? The expansion of row, right? So find row or column with many zeros. Find row or column with many zeros. Okay. Which row or column that you want to choose? Cuba type. Panas. So hot. Cofactor expansion, which row or which column? Which row or which column? Panas berpeluh-peluh. Okay, you can either choose row 3 or column 3. Let's choose. Remember I said to put the little arrow, so I know you choose which one. So plus minus plus minus plus, right? So you take lambda minus 5, right? And then you cross out, right? Then you get lambda minus 3 to lambda minus 3. Okay? Then actually this is plus minus plus. 0 times this minus 0 times that plus this times that. So you don't see the zeros because multiplying by 0. Ada yang nak column 3 boleh juga. Okay, if you choose column 3, I will write here ya. If you choose column 3, sama lah jadinya kan. You will get also this and you get also this. So in this case you get the same thing. Okay, now how do you get this? Is this minus this. Okay, so this is what I said that you have to know your factoring of polynomial. Don't multiply just everything out if you don't need to multiply everything out, because we want to factor. Okay, but we need to factor this. So you just take lambda minus 5. Okay, and then this becomes lambda squared minus 6 lambda plus 9 minus 4. Right? Lambda squared minus 2 times 3 times lambda, 6 lambda, plus 9. Okay, so this becomes lambda minus 5, lambda squared minus 6 lambda plus 5. You remember factoring? How do you factor? Dulu kat sekolah belajar macam mana? So, how do I do this? So, lambda squared becomes lambda and lambda, right? And then 5 factors of 5, there is no other possibility. Factors of 5 is 5 and 1. And this is a plus, so this is a minus, so you need both negative, right? Then when you multiply, negative 1, negative 5, you get negative 6. Okay. I don't know how you learn that at school, but this is how I learn to factor. So lambda minus 5, lambda minus 5, lambda minus 1. Oops, aku ni. Okay, so you don't need to multiply out everything. If you just do like this, okay, then this is your characteristic polynomial. Okay, so when you put f lambda equals lambda minus 5 squared, lambda minus 1 equals 0, you will get 5 and 1 as eigenvalues. Now we have to find eigenvectors with these two eigenvalues. Okay, later on you will see whether this matrix is diagonalizable or not. Okay, if you have 3 eigenvalues, you will definitely get 3 eigenvectors. Okay, then you will put the eigenvectors as a column. You will get 3 columns. Okay, later on that is what we will call it P. I just mentioned this now because then I have to erase. Okay, if we have 3 eigenvalues, you will get 3 eigenvectors. You call this P and you call this D, the eigenvalues, the diagonal. Okay, and in that case P inverse AP is D. This is next section. Next section is just to see whether you have enough eigenvectors to get the P, so that this is the eigenvalue corresponding to each eigenvector. If you do have these 3 and you have this enough, it is called diagonalizable. A is called diagonalizable. Alright? Now that is in the case when you have 3 lambda. This case you have only 2 lambda. Okay? So this is squared, right? You might get 2 vectors if you have 2 free variables. Like just now when we do row reduction. We will see later. If you get 2 eigenvectors with this also 1 eigenvalues, if you have 2 eigenvectors, there is another one from here, you will get enough eigenvectors for P. And your D will look like this. 5, 5, 1. Okay, this is the case because we haven't computed the V. If you have 2 eigenvectors for 5, so you have 5, 5, you have 2 eigenvectors. From the 1, definitely you get 1. If you don't, if this 5 has only 1 eigenvector, you don't have enough, you say A is not diagonalizable. Okay, that's it for diagonalizable. Okay, so now we will calculate. I just mentioned about the cases. After this, I will explain again. Yeah. Okay. Now I will erase this. Okay. I will also erase this. Okay, 5 and 1. 5 and 1. 5 and 1. Okay, so you have to calculate twice. So when lambda equals 5, you have 5I minus A V equals 0. Right? So let's V equal X, Y, Z. This is a matrix. This is solving a matrix. Alright? And by solving this for V, that is how we get the determinant, or the matrix, sorry, the matrix reduced. So now our matrix, just put lambda equals 5 here. Okay? So 2, 2, 0, but I get 0 at the end because homogeneous. 2, 2, 0, 0, 0, 0. So lambda is 5. 2, 2, 0, 2, 2, 0, 0, 0, 0. So see, there has to be at least one 0 row. But in this case, I have two free variables because this is equal. So I can do this. Right? This one I can just... Okay, so if I read this back, x, y, z, okay, y is free, z is free. So x, y, z equal, this one is x plus y is 0. X equals negative y. Y is k1, z is k2. So x is negative k1. Y is k1, z is k2. So if you take out k1, you will get negative 1, 1, 0. If you take k2, you get 0, 0, 1. Okay? So v1 is negative 1, 1, 0. v2 is 0, 0, 1. See, you have two eigenvectors with one eigenvalue. When lambda is 1, okay, put 1 here, follow this. When lambda is 1, negative 2, 2, 0, 2, negative 2, 0, 0, 0, 1 minus 5 is negative 4. Okay? Alright, so this is shortcut sikit ya. I will do a few. I think you can get this. 1, negative 1, 0. Okay, this one you just add, right? 0. Saya cheating sikit sebenarnya. This one, when I add, I got 0, 0, 0. I just put in the third row. Okay? And then this one I multiply by minus 1 over 4. So I get this. So dia ada dot, dot, dot. You have to fill this out semua. So x, y, z. So x minus y is 0. Y is the free variable. See this? This is the one that is not free. Y is free. Z is 0. Z is 0 come from here. Okay? X minus y is 0. That is a x, y, z here. Okay? So, first row, this column is not free. Go to the second row, you see this column, z is not free. When you read, z is 0. So it's actually the second column which is free. So y is k. Okay, so x, y, z equal, x is y, right? So k, 0. So you see this is from chapter 2. Now when you take out the k, it becomes 1, 1, 0. So v3 is 1, 1, 0. So these are the three vectors. Just now I mentioned that you will get these full marks if you check. Okay, so you can check. Tadi kita tak check kan? Try multiply minus 1, 1, 0 here. Check, minus 1, 1, 0. So this becomes 1, negative 1, 0, which is actually negative 1 times negative 1, 1, 0. So A V is equal to lambda V. Salah. No. This is wrong. Sorry. Your lambda is 5. So this is negative 3 minus 5, right? 5, 0. So this is 5, because lambda is 5, negative 1, 1, 0, which is A V is lambda V. Okay. Now with the second one, 0, 0, 1. So you try again with 0, 0, 1. Oops. This is still 5. So 0, 0, 0, 1. Okay. So you will get actually the last column. 0, 0, 5, right? 0, 0, 1, 0, 0, 1, so 0, 0, 5. So this is again 5 times 0, 0, 1. So check here. Now the third one is multiplying by 1, 1, 0. Okay, multiplying by 1, 1, 0. 1, 1, 0. So this meaning you add the first two columns. 1, 1, 0. So this is actually 1 times 1, 1, 0. So you are done with checking whether this is the right eigenvector to the right eigenvalue. Okay. Now you want to write P. So your P is equal to, okay, the first one is negative 1, 1, 0, 0, 0, 1, 1, 1, 0, with D equal, the lambda is 5, 5, 1. Okay, this hold on to this one until the next session, but this is now how to find the eigenvectors corresponding to the eigenvalues 5 and 1. So this is the whole of chapter 5. Okay. Alright. Okay. Oh, the eigenspace. So erase this first because this is not part of the question. Then you will put E of 5. Okay, this is because lambda is 5, is the span of negative 1, 1, 0 and 0, 0, 1. And E of when lambda is 1 is the span of 1, 1, 0. So this is the eigenspace. Okay. Next will be when you have different A. So let's try with another matrix. Okay. Before this. Exercise number 2D. 2D. Let's 1, negative 1. 1, 0, negative 1. 1, negative 1, 2. Okay, so alright, 2, negative 1, negative 1, 1, 0, negative 1, 1, negative 1, 2. So f lambda is lambda I minus a, so you put lambda minus 2, 1, 1, negative 1, lambda minus 0, 1, negative 1, 1, lambda minus 2. Then check again whether this is right. Negative 2, 2 becomes lambda minus 2, 1, 1, negative 1, lambda 1, negative 1, 1, lambda minus 2. Again, you see that there is no zeros here. Okay, so either you do row operation to get rid of sum to make it 0, or you just do the cofactor expansion. So if you do cofactor expansion, you have to do 3 times. So you will do lambda minus 2, right? Lambda 1, 1, lambda minus 2. Minus minus is plus 1. Right? 1, 1, 1, lambda minus 2. And then plus minus plus. Then 1, 1, lambda 1. Okay. And then determinant is now 2 by 2. So this is lambda minus 2, lambda, lambda minus 2 minus 1, lambda minus 2 minus 1, minus 1, 1 minus lambda, which is equal to lambda minus 2, lambda squared minus 2 lambda minus 1, plus lambda minus 3 minus 1 minus lambda. Okay, so this you have to multiply out, you have to add, and then it will be polynomial of degree 3, then factor and find lambda. So this is a little bit longer than before, but you have to go through and find the polynomial. Okay, and once you get all the eigenvalues, then you find the eigenvectors. And for the second part, which is diagonalization, okay, if you have enough lambda and enough v, then you get p and d. So A is diagonalizable if there exists P such that P inverse AP is D. So this depends on your lambda and on your vector, eigenvector. Okay, why do we need diagonalizable? We need this. If A is diagonalizable, you can actually find the power of A. P inverse A, P is D. Okay, try to find A to the K. A is P, D, P inverse. Why? You multiply this by P. You multiply this by P inverse. Right? P inverse is I. P inverse is I. So I is A. P, D, P inverse. Why do we need this? Because you want to find A to the K. Find like A to the 1000. Can you multiply matrix or get power of matrix until 1000? So doing this, D is just a diagonal matrix. You find the power of D is just the diagonal entries to the power. If you do A squared, this is like PD, P inverse, PD, P inverse, right? So PD, P inverse, PD, P inverse. P inverse P is just I. So this is just P D squared P inverse. You do this once again, multiply again by A, meaning you multiply A, this 3 times, P, D, P inverse, P, D, P inverse, P, D, P inverse. Then this again is equal to P, D cube, P inverse. So A to the K is actually going to the K, this is just P, D to the K, P inverse. So you get a formula to find power of A. P is from the eigenvectors, D to the K, so if your D is lambda 1, lambda 2, up until lambda K, D to the K is just lambda 1 to the K, lambda 2, call this N, up to lambda N to the K. Okay, and that is P, your eigenvectors. D to the K is just the eigenvalues to the K power. P inverse, you have to find P inverse by finding using row operation, or that's the other one for finding the P inverse. Then multiply, then you get A to the K. So this is the last one. Alright. Now what you have to do is to go through exercise in chapter 5, okay, and try as many, and also chapter 4, okay. I might assign one assignment or 2 assignments, okay, and give you time until we'll meet again. Before the final, I have to do one review, okay. Before the final, I will go, okay, your final, will be on 5th of July, okay, 2:30 to 4:30 p.m. right? And we have decided, instead of doing 3 hours, we'll do just 2 hours. And instead of going to the whole chapter 1 until chapter 5, we'll do chapter 3 after test 2, okay, chapter 3, chapter 4, chapter 5. Okay, there will be 4 questions. So chapter 3, not sure which chapter has 2 questions or mix. Okay, so chapter 3, 4, 5. Okay, we have some time. Chapter 5, the problem is you forget to do factoring polynomial, multiplying and factor polynomial and get lambda. If you fail to get the eigenvalues, lambda as the roots, you will fail to get everything like eigenvectors, P or D and so on. Okay. The last part I want to show for diagonalization is this part. Just now we have this example. A is 3, 0, 8, -1, right? If you remember, we did this twice already. We have 2 eigenvalues, okay, you have 2 eigenvectors. Okay, so your P is 1, 2, 0, 1, and D is 3. Accordingly, yeah, it is 1, 2, 3, 0, 0, and 1. Now, if you remember, we said A is diagonalizable because we have P and D. P inverse AP is D with this P and with this D. And if you want to find, say, question is, okay, how do I know this is right? One way you can check if this is right just now, right? Multiplying AV is lambda V, that is one thing. Another thing is you can check this. Multiply by P, you get AP is PD. Right? Multiply here by P, here by P. So cancel, AP is PD. Multiply AP, okay, this you will get 3, 0, 6, negative 1. Try PD. This is AP. Try PD. PD 1, 0, 2, 1. 3, 0, 0, negative 1. 3, 0, 6, negative 1. So you can check also this. 2, check. Now next question is find A to the 50. You cannot do it by calculator. Okay, calculator won't be able to multiply this. So what you will do is using formula, right? So just now we have P inverse AP is D, and this give A to the K. A is PD P inverse. So A to the K is P, D to the K of P inverse. So A to the 50 is P to the D to the K. D to the K is D to the 50. This to the 50 is just 1, right? What is P inverse? What is P inverse? 1 over 1 macam ni kan? Negative, negative, terlupa pula. What is the inverse of A, B, C, D inverse is 1 over AD minus BC. Ni tukar DA sini ke? Betul? Okay. So P inverse. Okay. So yang ini tukar, yang ni negatif. Balik lah pula. Okay, so this is 1, 1, 0, negative 2. Which is 1, 0, negative 2, 1. Okay, so multiply here, right? P inverse. Okay, so remember that you need this from also chapter 1. I said chapter 3, 4, 5, but still you need chapter 1, chapter 2. So it's actually the whole chapter. Okay, so here is this. So what is A to the 50? So multiply. This is 3 to the 50. Okay, 0. 2 times 3 to the 50. 1. I don't have calculator with me, so I don't need to multiply 3 to the 50. If you can multiply out and you get the answer, it's okay. But if you leave it like this, it's okay. this is 3 to the 50, 0, right? 2 times 3 to the 50 minus 2 and 1. If you can multiply, the calculator can do that, you can do it, and minus 2. If your calculator cannot do this, you just leave it like this, then this is your answer. Okay, so this is why we need diagonalization. If you don't have enough eigenvalues, say you have 3 by 3 matrix, you only have 2 eigenvalues. Okay, lambda 1, lambda 2. Just now, although we have 2 eigenvectors for here. So you still have 3 eigenvectors. So it's okay, diagonalizable. Some of the questions and example, it gives only 2 eigenvalues and 2 eigenvectors. In that case, you will write A is not diagonalizable. Okay? Alright, so I will let you know. Maybe Sunday is too soon for class unless you finish chapter 4 and 5. Okay, so your assignment would be chapter 4 and let me think whether you have to hand in or not. So you do this first. There will be another one, review class before. Okay. Done? Clear? This is not the last class. Okay, you still have this class. So this is not that hard. But chapter 5 needs lots of exercises, especially to find the polynomial. Okay, if you can factor out polynomial, you factor out first. Don't multiply everything out yet. Okay, what I mean is, sometimes when you do your polynomial, you get something like this. Lambda minus 1, maybe like something like this. And then you have another one, lambda minus 1 squared, lambda minus 3, something like this. Okay, if you have something like this, don't multiply out just yet, because this one is common. So you can just take lambda minus 1 first, and then the big one is this, and then minus, take lambda minus 1 from here and this. So this will reduce the power of 3. Okay, and just multiply this, and then just do this, and try to factor inside. This is already factored out. If you get something like cannot be factored linearly, then what do you do? If you have something like this, meaning the eigenvalue is only 1, because this will give you, Brian, don't say imaginary. There is no such thing as imaginary in the real world. So you just mention that this will give 1 real eigenvalue. So definitely you won't get 3 eigenvectors, because this one gives imaginary 1. So in this case, definitely it's not diagonalizable. Okay, so the trick is here. You don't have enough time, because 2 hours is not that long. Okay, so you have to know some tricks. Alright guys, have a good weekend. Okay, if it is not Sunday, it will be Thursday. So make sure you try and do all of this. If over the weekend I'm thinking of you to submit in your group, then you have to do that. But over the weekend, just try this yourself. Then you can compare with your friend whether your answer, why, probably if the answer in the back is different, probably there is a typo, let me know. Okay, otherwise you should be right. Compare with your friends. Okay, I have to look whether your assignment marks are okay or not before I decide whether you should send another assignment or not, because I have to still finish your marking of your test too. Alright, bye, take care, and see you. Okay. I'm also thinking of getting everyone probably one time for one Zoom meeting, something like that. At least we can see each other's face, right? Some of you don't get enough internet, but we'll try probably in our last class. Okay, bye.